Okay, so in today's lecture, some of y'all are, so in addition to the homework too, I'll also be posting, I'll go through and I'll actually publish the prior lectures onto YouTube later today as well. But besides that, everyone, with the exception of this slide deck, should have access to the slides we had already discussed. And once the slide deck is complete, I'll go ahead and share that so that you'll have access to this. So a final reminder is that the intro lab is due at the end of this week. If you haven't turned it in, do that. And I'll do a massive rollout before next class with all the other content that y'all are waiting on. So in today's lecture, what I want to do is pick up in chapter 2 where we last left off. We spent a decent amount of time articulating how we store data onto a computer system. And then we spent even more time articulating how we model numerical values inside of a computer system. So the next natural progression of this then is, how do we then take our numerical values and operate and process on them in meaningful ways? What makes mathematics so powerful isn't the fact that we simply have a representation of a set of elements like numbers, but we've defined a set of rules on how we can have numbers interact with other numbers to produce meaningful results. And so just as we've defined a set of rules in our abstract math and in our numerical maths that you can go ahead and compute a result, we can go ahead and have our systems compute on these numerical values to produce results that we'd expect them to. So we're going to subdivide the concept. We're going to, at least for this next subsection, section 2.3, we're going to look at defining arithmetic on our two different numerical data types we've defined in terms of our signed and unsigned values. And once we've inspected how that works, we'll then broaden our horizons and then see how is it that we can then represent floating point numbers, numbers that have radix points. And so we might continue a little bit of that discussion next class as well, because that's a very verbose topic. These are both very verbose topics, but ones that are fundamental for you to really understand how we get new values from current values inside of our system and what pitfalls can occur through that translation, that transformation process. Okay, so motivations that we have here, once we start talking about our integer arithmetic, is we want to understand how it works on our system so we can avoid at least two possible outcomes, adding two positive numbers and yielding a negative result. For sure, that is something that could currently happen. You could probably already predict how that might happen, but we'll actually see why that happens. And then also how the comparison between x being less than y might yield a different result as opposed to a comparison where x minus y is less than 0. So mathematically, those seem comparable. But once we start devising schemes, you could see why they might not be analogous to one another. You might want to be more specific when you go and lay out your logic. Okay, so let's start our discussion with unsigned addition. So let's consider, first of all, kind of a small explanation of what this means in our decimal maths, right? So consider two non-negative integers, our x and a y, such that we define our x and y between 0, because these are unsigned values, right? So the minimal value is going to be 0, and the maximal value is going to be based off of some word size, some bit vector of size w. So that's 2 to the power of w. Okay, so what we're doing there is we've limited our unsigned value towards a word size. So let's grab two viable word sizes. So suppose I had a word size of 8, so 8 bits. Then suppose I have the decimal value x as 39 and the y value as 233. Well, first let's quickly ascertain what is the max value that I can encode with a word size of 8. how high, if it's an unsigned value, then my starting value is at 0. So what's my maximum value before I have to move to a word size of 9? What's 2 to the power? How would I compute that, first of all? That's right. So the maximal encode, and since 0 is one of those, the maximal value I'd have would be, so that would be what, 255? 256 would be 2 to the power of 8, but I can't actually encode that value. I'd actually need a 9th word size because one of those values is going to be the 0. So I can go anywhere between 0 to 255. Okay, so with that said, suppose I had the values of 233, word size of 8, right? And the value of 39, word size of 8. Both of those I can encode. And in fact, the encoding of those is right here. And so whenever I preface 0b in front, that just means that that's my binary vector, my binary string representation of that value. So this is my value of 39. And notice I prefixed, so it was in fact 8 binary digits long, even though we don't need 8 binary digits to encode 39. And we're going to do the same thing here with 233. We're actually consume all 8 of those bits. Okay, now, one of the important things to understand about arithmetic is it's possible that the result of 2 valid binary strings, binary vectors, bit vectors that adhere to the predefined word size of 8 can result in a value that falls outside, beyond that scope, that goes outside of that range. And in fact, in this instance, we can see that our sum here would be 272. Or if I were to express that in terms of a bit vector, it would be this string right here. Now, the important part of this string is if I actually count the bits, we can see it's now going to have a word count of 9. And so that's going to be one of the rules that we're going to state in terms of our unsigned addition. If we compute their sum, we have the possible range of up to W plus 1 bit. So we understand that a addition of anything, in this instance of 2 8-bit values, can result in a possible 9-bit result. Not always it's possible. I also have an 8-bit result from that, but it's possible I might fall outside of that. Okay, so if I wanted to go ahead and visualize this unsigned addition, and so this concept that the result of a numerical addition with our unsigned values can lead to a concept in word size inflation. We'll formally define that in just a moment, but the idea of going from 8 bits to 9 bits, we've inflated the size of what we need to capture the resulting value. So depicted here, you see a 3D visualization. We are going to define, suppose, a function called add that takes in a word of 4 bits. So you'll see my sub value of 4 is representing the bit value, the bit count there. So I'm going to have a bit size, 2 bit vectors that I'm going to operate on, a u and a v. And this function just adds my u to my v. Right, so this is going to be my function definition here. So suppose I want to check the values that I put into my function and see what's the resulting value that comes out. And then I want to graphically depict that so I can see visually what that growth rate looks like. So what you see here, I have my u, which represents the values I have that I can encode with 4 bits or with a word count of 4. And so similar here, I have my v, which is also a bit vector of word size 4, which means that I can have a minimal value of 0 or a maximal value of up to 15. And since the function revolves around adding those together, the the sum access that you see here can go up to 32, right? Because if I can have a maximum of 15 and I have another maximum of 15, you'll see we have a linear growth rate. And so here clearly sum is outside the 4-bit word count size of both U and V. And so this kind of visually represents how we've inflated the size of our vector based off of our two independent access points. Oh, yeah. Oh, yeah. Yeah, we'll go through the actual mathematical principle of what we'll then consider a normal result versus an overflow result. So we'll create a delimiter between what happens once inflation occurs. And of course, let's formally define what word size inflation is. So the resulting word size inflation means we cannot place any bounds on the word size required to fully represent the results of our arithmetic operations. And then we can kind of get a idea here. Let's see, we see here, this is if I trace the line here, if this is 32, we should be able to get to a max value of 30 if we want to articulate. And because our starting value is 0 to 15 and 0 to 15. So the maximum encodable numerical values for a bit vector of word size 4 would be a total of 30, which is a word count 5, a word size 5. Okay, so let's talk about then defining how can we go ahead and then produce an arithmetic operation that adheres to the word size. Because if we have this word size inflation in this instance, it results from moving from a word size of size 4 to 5. But see that can arbitrarily grow out. All of a sudden, if I had took that result and then added it to one of the original values, then it can keep growing and growing indefinitely. So we need a mechanism that allows us to ensure that after we've produced a result, that the result is in the same word size that we're operating within. And of course, the most obvious way to do this is to truncate, right? To be able to take whatever the result is and you chop off down until you have the word size that you need. So we're going to define what's called modular arithmetic. So a modulus type of operation, which means it allows us to circle back to where we started from. Okay, so let's define our modular addition for our two arguments, x and y, where they fall in between that word size value, the appropriate encoding we can actually have based off of our w bit vector, or w size bit vector. So when we go to truncate our w bits, we're going to keep starting from the least significant bit up until we get to our word size. That's what we're going to keep. Everything that falls outside of that, we would truncate. So we truncate the prefixed values, the values that fall on the left side. So an example of this, suppose I took the value of 9, which I can encode as a 4-bit binary vector. And let's suppose I took the value of 12. My binary representations then are these two bit vectors here. And suppose I call that sum function, where we add those two together. That would result in a value of 21, which is a 5-bit representation. So if we discard the highest bit such that we get back a 4-bit vector, we would then drop this 1 and we would have the value 0, 1, 0, 1, which would then represent, or it would, in terms of a decimal evaluation, would be the value of 5. Which, if I took 21 and I mod that to 16, which is 2 to the power of our W, right? 4 is our W, then the mod of that is 5. So the same kind of concept that drove the modulus division you probably had to make use of in 1583, that concept is how we go ahead and ensure that the resulting value, well, not the same concept, but a similar concept, ensures that the resulting value is going to fall within inside our word size that we're looking for. Okay, so let's look at the mathematical principle of this, because we're not guaranteed to get any word size inflation. So what governs our word size inflation is, suppose given an x and a y that fall between our actual encodable values. So if our W is 4, that would be between 0 and 15. Then we go ahead and produce our unsigned addition operation. So we add those two bit vectors together. And then we can check the result of that value. If the result is less than the max value we can encode, then it works like normal. We did not fall outside the range. Now, if the result is in between the max value from our word count being, in this instance, 4, and the next size up, so the word count being 5, because with addition you can't, it's going to be of size W plus 1 if you have an overflow, then we consider that an overflow condition. And then on instances of overflow, you truncate. But if you treat that as a normal addition, it's going to read as a value as if you've actually like reduced an amount when producing an addition, right? So it's going to be kind of an anomaly, but it's one you can detect, it's one you can look for.
That kind of reminds me of discrete.
Oh, well, yeah, I'm glad, because I think probably one of the skill sets that you should come away with discrete math is being able to interpret and read mathematical expressions, statements, and proofs, right? And so a lot of the algorithms that you'll learn how to implement actually have a basis in formal mathematics. So being able to read formal mathematics and then re-express them in terms of computer software as code is a really valuable skill to have as someone seeking a computer science degree, because it'll allow you to go ahead and make implementations based off of concepts that are like discussed mathematically, if that makes sense. So yeah, if this looks like discrete mathematics, it should, even highlighting the fact that this is articulated as being the mathematical principle that formally defines what it means to have unsigned overflow. And again, it just is stating mathematically what we more informally kind of talked about these last couple of slides. Okay, so what's a good way of visualizing how this might look? So an arithmetic operation is said to overflow when the full integer result cannot fit within the word size limits of our data type. And so what you see here is this black arrow represents these issues where we have no issue, where the result of our addition stayed in the same word size as our starting bit vectors. Now, where we have issues is right here. This is a threshold. This is where we start to eclipse past that original word size, and we require one additional bit to encode precisely the result. And the way we can handle that is by truncating it. It just forces us back into some encoding that fits into the original word size. But typically, by removing your most significant bit, it's obviously going to make it less than what you probably had in terms of your addition prior to that. So let's do that same visualization. Before, we showed a visualization that allowed for our inflation, our word size inflation. Let's look at the same visualization that now does not allow inflation, and in fact then encodes using the overflow mechanism we talked about. So here, suppose that we set our word size to be 4. So we have 4-bit vectors and we can't grow past that. So that means we produce a normal result, a non-overflow condition on the instance when our X bit vector and our Y bit vector resolve to a value that's less than 16. So anywhere between 0 to 15, we're good. And then when we eclipse 16 or go higher, notice when we visualize, we're going to drop back down into the same encoding space here and start building back up. So that the highest value I have along my sum axis is going to be scoped the same as what I have on my U and my V axis. Okay. So let's talk about unsigned arithmetic overflows, especially as they relate to C, the C programming language, the one that we're learning how to use. So when we execute our C programs, overflows are not signaled to zeros, right? They occur, they're valid. And so when you go to detect an overflow in C, you can think of this as, well, checking the values before and after your operation. So again, suppose that we're given the unsigned, the values of X and Y. And then, so since they're unsigned values, since there's no value that's less than 0, it should be true that X plus Y is either greater or equal to X. It can never be less than X, right? Because there's no way of subtracting using addition. You don't have negative numbers to add to your X to make it go down. So we can assume that it's true that this first expression, that this is a true expression. It might be that Y is 0, so that means X could be equal to X, but it could never, or it could be greater than X. If Y is any other value besides 0, then it's going to be greater than X. Okay, so if we accept that that's true, then we can also say, so if the sum S did not overflow, then the sum should also be greater than or equal to X. And all we did here was we replaced S with that expression X plus Y. Now, we can detect an overflow because if our S is mathematically less than X, then that meant that we dropped a most significant bit and we re-encoded in a value that was less than what we started with. And this shows you just a mathematical expression, very simple arithmetic that gets us to show that S is less than X if an overflow occurs.
To see if we could work out how to detect an overflow. Just thinking it out. That's like what would you do to test if the integer does it overflow?
That's a very interesting test question. What class was that in? Oh, excellent. So these are concepts that y'all covered already in Java 2 then as well. And good one to kind of start getting you to think about then, motivating these concepts. Okay, so that's unsigned arithmetic. And the nice thing about unsigned arithmetic is that it does start at 0. There is no sign that can cause an addition to act like a subtraction. That could allow for overflow in multiple directions. So now let's talk about that. Let's introduce the concept of signed arithmetic. So again, our format of signed values is with 2's complement. So 2's complement addition has to decide what to do when the result is either too large to encode, So that's like the overflow that we just saw with unsigned addition, or when it's too small to represent. That's when it becomes negative, or it's too negative, which is like addition in the reverse order because we have the sign to consider. Okay, so let's redefine some of our criteria here. So suppose that we're given the integer values of x and y in the range of, and so we're going to adhere to the same scopes that we had already talked about when we introduced the concept of 2's complement. So we already said that some given x or some given y has to be minus 2 to the power of w minus 1. And then here, the most positive side is almost the same, but we take 1 away. We have to subtract 1 because 0 counts as a non-negative value, right? So they're not completely symmetrical in that regard in terms of positive versus negative, because 0 counts as a positive term. Okay, so we've already seen that. And since now we've shifted the number of encodable values we have to the left, right? Because we don't start at 0, we now have a minimal value where half of our values are negative and the other half are not negative. Then that means that when we go to check what the sum in the range is, notice that potentially, if we allow for inflation, our word size inflation, we could get anywhere between minus 2 to the power of w all the way up to 2 to the power of, I don't think that this is, there we go, 2 to the power of w minus 2. And again, this could potentially require us then to have an additional bit that results. So an inflation occurs. And once inflation occurs with one operation, it's possible to repeat that process and just indefinitely inflate. So when we look at these mathematical expressions, then we're like, oh, we're going to have to use the same thing that we did to fix this in unsigned arithmetic. We're going to have to find a way to get the result expressed in the same word size as our original input values. And so we'll take a similar approach. We'll truncate that. And we'll take a similar approach in the fact that we'll truncate the most significant bits and we'll only look at the least significant bits, because that starts producing a value that's akin to a modulo value. And then you could do detections to see if an overflow occurred or not. But those least significant bits are still carrying the values of the summation. They still represent the correct bit orientation. Okay, so with sign truncating, though, we have to avoid, again, our ever-expanding data sizes. So we truncate the integer with w bits long, that's what I just said. But then this is where we deviate from unsigned. We have to take the result and we have to parse it. We have to interpret it as a 2's complement number, which is obvious, right? Because that's the data type we're currently looking at. Okay, so let's look at the mathematical principle for our signed arithmetic. It looks very similar to our unsigned arithmetic, only notice we've introduced a new term. So where the prior evaluation had us have a normal condition and an overflow condition, now we know that there's a normal condition, a positive overflow, and a negative overflow. We get a positive overflow if the result of adding our 2 bit vectors together resolves to be greater than what we can encode. It's a normal condition when the bit size remains the same, and it's a negative overflow if we have to increase the bit size by 1, but it's because of a negative value. It goes below our minimal encoding value. Okay, so if I were to graphically illustrate, how can we get all possible outcomes from signed integers adding together into either a 4-bit or 5-bit word in the case where w is equal to 4, or in this illustration where it's w to the power of it's 2 to the power of w, and mapping it into the space that is encodable, which is going to be for a signed number 2 to the power of w minus 1. You can see my threshold here is in my encodable space, and this is the set of results I can have. So where I have my black arrows, that's going to be case 3, and that's going to be case 2. No overflow occurs. I can treat those. That's the normal range for my 2's complement numbers in W bits. So I don't have to do anything exceptional. Now, my exceptional cases occur in case 4 and case 1. And in this instance, I have a value that's too negative. It's 5 bits that has a leading value of 1, or I have a 5-bit term that has a leading value of 0. And so I'll just do what I did before. I'll go ahead and truncate, which effectively the truncation, the effect of that on a negative overflow is it's going to add 2 to the power of whatever w is to my sum. So I'm adding something to my total so that instead of being too negative, it picks it up so it falls within my encodable range. Or if it's too positive, I'm going to subtract from it 2 to the power of w. And of course, I'm either adding or subtracting 2 to the power of w if it was so if it was a 4-bit word, I'm either adding or subtracting 16 because I'm adding or subtracting the most significant bit, which is going to force the value to fall within the range that I want it to. Okay, so let's take a look at what that actually looks like as some examples. Can everyone see this? Is this too small for you to see? Just out of curiosity, perfect. Okay. So again, I have my cases. So let's look at these columns. I'm going to have my given inputs, and we're going to be working with word sizes of 4 to make it easy. So I have my X column and I have my Y column. And then I will have my X plus Y as my third column. And then I'll have my X plus Y where I'm truncating as my fourth column. And then I'll delineate when I've hit what type of case, whether it was a normal case, whether it was a negative overflow, or whether it was a positive overflow. And then even with my normals, I could say whether it's a negative normal number or a positive normal number as well. Okay, so let's look at this first row. Given a -8 and a -5, let's see if we can't define our terms in fact as well. So while we're reading through this, what term is going to, what's the most negative term I can have in this instance? Maybe instead of, maybe what we can do is look at this slide and jump back. Oh, so in this instance, so what I was asking for, and again, we'll look at the other slide and then we'll come back to make sure that everyone's on the same page. So when we look at this, I want everyone to be able to kind of understand the rationale. So I'm not just explaining a table filled with numerical data. Like I want you to make the connections between that. So this is a leading question for you. We talked about how there's 4 different cases that can result in signed integer. A case where I get a 4-bit, a appropriate range, normally scoped value that's positive, right? So I have a bit vector, I add another bit vector to it, and it results in a bit vector of the same size. That's good. That's within range. That has not mutated my bit vector in any meaningful way, right? Now, if the resulting value is positive, that is one way I can get a result with my signed values. Now, if I took my X term, I took my Y term, I added them together and got back another 4-bit vector, but it was prefixed with a 1 as the most significant bit, then that's a negative value, but that's still a normal value. So I have two cases that are a normal negative and a normal positive. The exceptional cases are when I take my 2-bit vectors, add them together, and it resolves into now a word size that has to be 5 bits to encode. Now, those are overflow conditions. And when I have signed numbers, my overflow conditions can occur because it's either too negative to encode or it's too positive. So if I have a bit size of 4, and if I'm using the 2's complement encoding style, what is the smallest size number? What is the most negative number that actually fits within my range? All right, let's think about this. It's going to be, I have my entire scope. So first of all, what's the amount of permutations we have? So 2 to the power of 4 is what? It's 16. That means I have 16 different encodings, representations. So with an unsigned value, it's between 0 to 15, right? Now we said with a signed value, we're essentially not starting at 0. We're going to take half those values and slide them into the negative space. So 0 to 15 has 16 different assignable symbols, right? Assignable elements, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 16. Now we said half of those are negative, half of those are non-negative, right? So half of the 8 elements can potentially represent a negative number, which means what's my minimal value? -8, right? -1, -2, -3, -4, -5, -6, -7, -8. 8, half of my encodable binary combinations will represent values in the negative space. Which means, what's the maximum value starting if I counted? I have 8 more encodings, right? And if I start at 0, what's the maximal value I can have? So, okay, so that means when I produce an addition with a word size of 4 on a signed data type, an overflow occurs if I ever go below -8, that would be a negative overflow, or a positive overflow would ever occur if I get a resulting value above 7, right? Anything in between, and that's a normal outcome because I can encode it with 4 bits. So are we all on the same page? Perfect. Okay, so now with that said, let's just look at this table just to firm this up. So suppose that I have -8. So that's the most minimal value I can have with this encoding, right? And then a -5. Those are both legal values. I'm going to add those together, and that's going to produce an outcome that's -13, which it's impossible. I cannot encode that with a word size of 4. Now, if I allow for inflation, I can, right? So the actual outcome represents what we would normally expect it to if we were unbounded. But if we bound ourselves to have a bit size based off of 4, then we would do a modulus addition, which means we drop the most significant bit, which means our outcome will be 3. And then in that instance, then we would know if that occurs, oh, that was a negative overflow that occurred. Okay. Let's look at this again. I'm going to use the decimal numbers because I think everyone thinks in decimal numbers probably with arithmetic. But just so you know, the binary representation is directly under. So when you're looking at this table, just know that you can confirm the decimal to binary translation between these two. Just so you can see, all I'm doing is truncating that most significant bit, and that's how I'm getting that decimal result that I'm talking about. Okay, let's look at this next condition where we have a -8. That's the most minimal value I can encode. I have another -8. That's the most minimal value I can encode. So if I take the two most minimal values and add them together, I'm going to get -16. And so with -16, notice I can't get any smaller than that with two 4-bit words. What's the size it takes to encode that? 5 bits. So that's an illustration here that with addition, even if you have the most maximal values, it'll only ever result into a word size increase of 1. Okay, now clearly -16 is we can't represent, so we will truncate that, in which case our modulus addition is going to give us 0. In which case, that was also a case 1, another example of a negative overflow, but one that showed you what happens when we take the most minimal values and add them together. Okay, let's do this again, but with something more normal, right? Let's take -8, our most minimal value. Let's take 5. The result of that's going to be -3. -3 is still a 4-bit vector, so it's in the word size. The resulting word size is the same as our initial word size, so we consider that to be a normal outcome, but results in a negative value. So we'll call that normal negative. And very similar, if we have a value of 2 as our x term, a value of 5 as our y term, and we add those together with in our unbounded and our non-truncated value, it's going to be 7. Well, 7, even if we truncate it, is still going to be 7, right? So that's another instance where we hit a normal case, but in this instance, the resulting value is positive. So notice we can have two normal cases, one where the result is negative, one that's positive. And then finally, we will have, suppose we have the value of 5 as our x term, and then 5 as our y term. And if I add those together, I now get the value of 10. Now recall the maximum value we just stated earlier for our word size was going to be 7. Thank you. So here in this instance, we would take our result. We would truncate the most significant bit, and our result is going to end up being -6. Because what we're doing with that is we're taking that and we're going to subtract from it the max value. And so that's going to be our case 4. So yeah, so notice when we take a value away, or if we add a value, it's going to allow us to compress it back into that result. So if I want to visualize this behavior, so we walked through it, we talked about it, it's probably kind of abstractly in your mind right now. Let's actually visualize what this field looks like and how it now deviates from the visualization that we saw from our unsigned addition. So here we have 3 conditions we care about. So suppose that we have, again, our word size 4. Yeah. And so here, just to keep the numbers in alignment, notice what I'm going to do here is I'm going to use an equal then and less than on my negative term, but a strictly less than, I'm sorry, greater than, and equal to or greater than, or less than, doesn't matter. I guess it depends on what viewpoint you're looking at this from. We have to fall between this scope, and in this, you can be equal to -8. In this case, you have to be less than 8. But that gives you that nice symmetry that you like. Oh, that I like. Okay. Anyway, with that said, as long as it falls within this scope, then this is the behavior we expect. This linear behavior. But again, the concept of any kind of modulo arithmetic is that when you hit a max, there is a max value, and then you reset and repeat at whatever the minimal value is. So there, it allows for this idea of cycling through. So since there's a limited amount of encodable space, and the result could potentially be up towards like 2 to the power of w plus 1 or whatever, right? Or w in this case, since our expressible terms is 2 to the minus of W minus 1, then we have to find a way of re-encoding. So here, if we have our negative overflow, then we see we capture that behavior here. And if we have our positive overflow, we have captured that behavior here. So just a way of visualizing what's happening there.
So if the mod is just going to be the word size. Sorry.
That's right.
2 to the power of the word size.
That's right.
No matter what it is, if it's 10 and it's 10 to the power.
Yeah. And so again, the goal here is that you want to have a function where the resulting data size is the exact same as the starting data size, so that you don't have word size inflation. So it's always about trying to figure out, how do I keep the same space I started with?
Signed overflow undefined behavior.
What was the question?
Is it unsigned overflow undefined behavior?
So it's not flagged as an error, right? It'll allow you to run that, but there's still flags that occur. So so it won't prompt you if you have an overflow, but you can typically detect when there is an overflow, and you can actually have, like, for instance, when you were in assembly, right? You were able to check assign an overflow flag to see if an overflow occurred.
I mean, like you can have sorry, but doesn't that mean, like, if this does happen, you can have like weirder effects?
Yes.
Like,
yes. Absolutely. That's why it's important to understand what's happening here. You know, a lot of systems that you implement already kind of do these detections for you, and they handle a lot of this. And a lot of instances, we're talking toy examples with these, with a word size of. So let me give you like a meaningful kind of understanding. Right now, we're doing very small numbers, so we can talk about this. But have you already encountered taking 2 really big numbers? Because the actual numbers we're talking about encoding are usually on the order of 32 bits or 64 bits, right? And have you experienced overflowing those before, where you've taken 2 terms and either added them or multiplied them together and gotten a result that you didn't expect it to be? Like, I'm asking the class in that regard. Oh, interesting. So no one's actually experiencing. So in a lot of systems, it allows you to overflow, and this is the behavior that it would do. You can go ahead and detect for that. And like, for instance, let me see. Let's see, actually, let me see if I have, out of curiosity. I'll even check Java really quick. See if I don't know if I have JShell on this machine, because my other machine died and this is an old one. Nope. Okay, no time. Yeah, my monitor went out on my other computer not too long ago, so I'm on an old 2013 machine and I have to configure it. We'll play around with some examples. Remind me next class to prime up some examples to illustrate actual overflow. But you can actually overflow even in a lot of the higher level languages, and it just produces the computation the way you would expect. It produces a result with you thinking without alerting you that anything occurred.
I mean that, like, if you try to, for example, make a program that tries to detect overflow, so you're using signed integers and you optimize it like with a smart compiler, there's a chance that the compiler, because it's undefined behavior, will just assume.
No, yeah, of course, yeah. You can put checks in place. You can even insert logic of your own design in higher level languages. We're not even talking about system level languages. And these detections are based off of what we were talking about earlier. There are conditions where you know when it falls into a normal case or when it falls into an overflow case. There are mathematically defined definitions that you can check the state of your binary sequences, your bit sequences, before and after the computation and know, oh, an overflow occurred. And then you could do something in response to that. But what you should know is that there is nothing that like prevents that from happening. The standard behavior of these truncated arithmetic functions is simply to drop the most significant bits that aren't part of the encoding that it's working with. So if you have a word size of 4, it'll do the addition as if it is limited to a word size of 4. So the combination of everything up to the overflowed bits is right. And the only thing you've lost is the overflowed bit. And actually, since it's arithmetic, and then you know what it's only one bit you're losing. And if you know what an overflow value is, if it's an unsigned value, you know that there's a 1 that has to be prefixed onto it, or a power of 2 to the power of whatever added to your term. Or if it's a signed number, you can check to see if it's a 0 or 1 that gets truncated, or you could see if it was a negative overflow or positive overflow, and then predict what the missing bit is. So there's definitely ways, right, to be able to retranslate that value but it doesn't do that. Like the system doesn't do that. It just is encoding onto the word size that it was given on.
I mean that the compiler itself might just get rid of your check.
Oh, I see what you're saying. Yeah, but there's ways you can still go ahead and do those detections. I see what you're saying. So you're saying if you put your protections in place, and since it's an unchecked, your compiler won't simply go ahead and implement them for you. But what's more important at this point, before we actually start talking about how these are implemented at the system level, is just understanding this is how you do this math and restricted to a particular word size. You just the operations assume that you drop the most significant bit, and that forces an encoding that's modulo, which means that you can have. It's interesting, right? Like once you have a function that is cyclical, then you could have multiple inputs that lead to the same result, right? So like, for instance, on a situation where a overflow did not occur, you have the actual valid value. And if it did occur, it maps to a value that you don't expect it to be. But it's still a valid value that's encodable in your binary space. Okay, anyway, this is just kind of talking about how we do our 2's complement addition. Let's talk a little bit about 2's complement in general. I don't know if we ever really talked about what 2's complement is, what a complement is. I'm assuming you discussed that a little bit inside of your assembly class, because you probably had to do binary addition and multiplication, I would think. So I guess we'll just kind of recover those concepts very briefly. So when I say 2 complements negation, let's start by saying it's going to give the complement for a given signed number. So the complement mathematically is the number's additive inverse. So in decimal mathematics, if I had the value of 5, right, minus 5 would be its complement. That resolves to be 0. That's the additive inverse. Or if I flip that, the complement of minus 3 would be 3. So we just reverse the sign to get the complement in our decimal mathematics. Now, with our bit vectors, it's similar but not quite exactly the same, because there's not as much symmetry in the way that we encode our bits. Remember, we have half of our encodable bits as being negative and the other half as being non-negative, where 0 represents one of the non-negative terms. So with that said, with bit vectors, we find its complement by flipping the bits. So for every 0 bit inside of its representation, we can flip it to a 1. And then from that resulting value, we add 1 to it, right? Because it's 1 unit out of alignment between the actual inverse additive and its complement. Because 0 is its own complement, right? So does that make sense for everyone? Does everyone remember doing that in assembly? Like kind of representing your complement by just flipping bits and adding 1 to it? Was that a activity that? Yes, no? Is this foreign? I guess, is this a new concept or is this? Okay, perfect. But that's how I translate. But I guess the big takeaway is, and maybe if you didn't cover it in assembly, let me just make sure everyone kind of understands what it means to be doing that. The goal is, how can I take a binary representation of a signed number and re-express it based off of its complement? So how can I take 5 and then convert it into -5? So that if we're doing basic decimal arithmetic, we can get like, if I add those together, I should get 0, right? I should get the additive inverse. And so the process, there's a very easy process. Like, it's a brainless, it's a mindless process, right? Like, I don't have to have any intuition. I could just flip the bits. So just all 1s to 0s, all 0s to 1s, and then whatever the result of that, add 1 to it. And that produces, for me, what I call the complement to my given number. Okay. So if I wanted to negate a number, because normally when we talk about negation, that's like applying a minus sign, right, in front of a value. That's like making a positive value negative or a negative value positive. That's how we do it with sign numbers. So we're talking about arithmetic already, right? The reason why I want to talk about negation is to illustrate how can we make a number go negative. And just remember that subtraction is just addition with negation, right? Subtraction is just addition with negative numbers. So to say, right, 5 minus 3 is the same thing as saying 5 plus minus 3. So there's nothing special we do to implement subtraction. Okay, now the special case that we should be aware of is if the number is the smallest possible in our range. So our lowest negative, our minus it on a 4, on a word size of 4, that would be our -8. Then the opposite itself, in our range, which is the lowest negative value, its opposite is itself, which means it doesn't change. Okay, and of course, the reason why we do this 2's complement this way is just because that's how we store our numbers inside of our machines. Okay, so if I want to take a quick example of what negation looks like, let's take a look at this table. So suppose that I have my bit vector, okay, represented as a series of bits. And let's say that we have a word size of 4 on these examples. I have my original size here, and then my negation symbol is the tilde signal here. Or I'm sorry, not the negation, but it's going to be the flipping of the bits. So we're going to flip the bits, and then we're going to increment by 1. That's going to give us the complement. So here, if I were to start with 5 and simply flip all the bits, it's going to make it -6. When I increment -6 by 1, that gives me the -5. So this is just showing you the logic actually works that we talked about. If I started with 7 and I flipped all the bits, so the 0s became 1s, the 1s became 0, I then suddenly get -8, and I increment that 1 by 1, that gives me -7. If I start with -4, flip the bits, that gives me +3. I increment it by 1, that gives me the +4 that I'm looking for. If I start it with 0, I flip all the bits, all the 0s to 1s, that gives me -1. I increment by 1, that gives me back to 0. And then finally, this is the case where I start with -8, I flip all the bits, add it by 1, and I get back to -8. So that's the one special case with 2's complement, right? Everything else actually acted as the complement term, like the additive inverse, except for -8. Yeah, and 0 too. But 0 is actually, that makes sense though. 0 is its own additive inverse mathematically. Whereas in this instance, this is kind of an outlier. But since 0 is, then that has a weird result where so is -8. So does everyone see how that's kind of weird? Outside of the way you would normally think of mathematics? Because like 0 minus 0 is equal to 0, right? 5 minus 5 is equal to 0, right? Here though, -8 minus 8, that does not work as an additive inverse. Okay, let's move away from negation. Let's move away from addition and subtraction because we've introduced the idea of negation. And let's talk about multiplication. So if we were to look at bit vector multiplication, let's look at how you probably did it inside of assembly. This is where you kind of wrote out one term, one bit vector. You probably wrote out another bit vector underneath it. And then you're like, oh, all I have to do is I take the first bit. It's kind of like doing long multiplication, right? So you take your first term and you apply it. So 0 times 0, like 1, 1, 1, 1. Yeah, it's going to flip all the bits to be 0. And then I take my second term and I shift it over by 1, just like I'm doing long multiplication. And then I'm going to go ahead and produce, well, 1 times this is going to repeat itself. So it's going to produce the same value, 1, 0, 1, 1. And then I take the next term of 1. I'm going to shift it over 2 spaces. And well, since that's a 1, it's just going to replicate the series and I'm multiplying on. And then I have a series of 3 results where I then sum them together. And now when I sum them together, that can produce terms that carryover terms. So the result of my 11 times my 6 would then result in the decimal value of 66, which can be expressed as this binary term, right? Did y'all, just out of curiosity, did y'all do that in assembly? Kind of actually do binary multiplication by hand? And if you didn't, does this concept at least make sense? Notice you're doing the same thing you would do with decimal multiplication, but it's easier, right? In my opinion, it's easier to do with binary values because it can only have 1 of 2 states at any place. Okay. So let's talk about multiplication. We're not going to go too deep into multiplication on outside of what you already did in assembly in terms of mechanisms, at least initially. We're going to talk about more or less like shortcuts on how we can try to do this. So the big things we should learn about with unsigned truncated multiplication, again, just like we had to redefine our addition functions to guarantee that the word size remained the same between my input and output terms. We have to do the same thing with multiplication. But multiplication, I think, is far, far worse than addition because it can produce potentially much larger word sizes than what addition can produce. So how do we handle this? How do we handle the fact that you could have a massive increase of your word size? Well, in C, our unsigned multiplication is defined to provide a W bit value. That means that we maintain the same value as what we started with. But you could potentially have a product, right, of up to 2 to the 2 times W bits. So you can get a remember, addition could do W plus 1 bit increase. The maximal result from a product of 2 bit vectors is 2 times W, which is it's like taking and doubling the size of whatever your word size is. That's a lot of values that you can encode. So we're going to do something similar, though. We're going to do a modulo operation to ensure that we're inside of the 2 to the power of W, ensuring that the result fits within our bits. Which means we just chop off everything that's on the most significant bit, right? And we just re-encode using the least significant bits. The idea is the same. And here this slide says pretty much the same thing. Only the difference between our signed multiplication and our unsigned multiplication is that the most significant bit actually does matter for whether it is a negative or positive product. So we do have to keep that in mind. Okay. So let's take a quick look at our multiplication with both unsigned and two's complement. So suppose, for instance, we had here, we're going to have our word size equal to 3. So we can see if we had 5 and 3, the result 15, we would need at least a word size of 4 to encode on unsigned here. Oh, actually, we could probably do it in 1, 2, 3. This is a 15, yeah. So word size of 4, and we'll truncate to be word size of 3, so it'll actually get represented as a 7. So again, concept behind how we're handling addition and multiplication ends up being the same way in terms of how we're preserving our bit sequences. You know, we can look at this again. -3 and 3 is going to result in -9. You truncate, and that's going to be your 1, 1, 1. But now, since we're using this as signed, we would treat that as a -1, as opposed to unsigned, which is the 7. So the way that we are parsing this just depends on the type of data that we're looking to examine this under. And so in the instances that we have 9, 9, and these are all pretty consistent, right? I'm not going to keep walking through. You can feel free to kind of look at the tables as you want. Okay. So I showed you the example of how multiplication would actually work. And you could probably guess then that it's slow to do multiplication. It's slow to do division as well, right? So addition, subtraction, bit level operations, shifts take one operation to do. But if multiplication requires you to examine the results of each bit in a operand and then sum all the results, you can see how that could easily take, say, 10 or more cycles to perform. So what compilers typically do is they optimize any kind of multiplication operation by redefining it as a combination of shift operations and additions. So, and intuitively, you can kind of see how that works when I laid this out earlier here, where we're shifting our sequences across and then just adding them together. And of course, the compiler does that, so it's invisible to us, but understand that's what's happening. And I think with the data lab, you might be tasked with doing kind of producing results like multiplication restricted to things just like shift and plus, so that you get a better understanding of what the compiler's doing to optimize things like multiplication and division. Okay, so, yep. Okay, so with that said, if we're shifting the behavior, the effect of shifting your bits over, shifting bits from a lesser significant bit to a more significant bit, like shifting to the left, has the byproduct of multiplying something by a power of 2, right? So a 2 becomes a 4 becomes an 8, and 8 becomes a 16, right? We can exploit that. That's a very easy operation that resolves into a multiplicative property. And the interesting thing about this is we already talked about the overflow behavior on multiplication. When we go ahead and truncate, we remove all the significant bits. Now, if we're doing left shifts, and if we're doing true multiplication and just trashing those most significant bits, the after result, the overflow behavior is the same. The end result is the same. And if that's what's actually the resulting value, the truncated value is what we get back in result, then that's why we can use shifts and then arithmetic operations in replacement of true multiplication. And because we get the same byproduct of the modulus that results from that. So an example of how our compiler might optimize is, suppose I had x times 14. I could re-express that as this linear equation here of shifts and arithmetic that produces the same result. And so that reduces the very costly multiplicative property to be just a collection of these shifts, additions, and subtractions. And again, the end result would end up just being whatever the modulus value is in both cases. Okay, let's talk about dividing. We talked about multiplying. Now, unlike with subtraction, where subtraction is merely the addition of negative values, division has a very different kind of outcome. However, we can shift right, and it has the byproduct of dividing our value by a power of 2. So our 8 becomes a 4 if I shift by 1 unit to the right. And you can see this increasingly decreases by a power of 2 the more units I shift. So the same way we can optimize our multiplication using shifts and addition or basic additive properties, we can go ahead and encode division in a similar mechanism by exploiting right shifts based off of powers of 2, though. So some examples of this, and let's actually look at this in particular with a with 2's complement, because 2's complement has kind of a weird result that we're going to have to correct for. The result, if we try to just do our left shifts using 2's complement, means that we round down instead of truncate our divisor. So let's see what this is. So suppose that I have, for instance, these binary sequences, and I'm going to shift them to the left by k amount. So my k amount is 0, shift 0 units, shift to the right. Shift to the right by 1, shift to the right by 4, and shift to the right by 8 places. So if I start it with a decimal of 12,340, I'd of course result in a value of 12,340. I'm going to represent that right now as a floating point number because that's what happens with division, right? Divisions are fractional. I'm not guaranteed to have so I want to show you what the actual value is so we can compare and contrast. So let's shift it by 1 and notice I have my decimal place and the actual value. Notice that does a great job of producing division-like behavior. Let's shift it over by 4 and notice here I'm truncating. So the actual value is 771.25. Integers don't have fractional numbers, so this does a good job of encoding that into a 771, right? Oh, I'm sorry. Yeah, this is unsigned values. So this is all correct. This is working as expected. If I do 8 values, 48.2, I truncate into an integer number, I get 48. That's exactly what. So I get the unsigned integer division the way I expected to, simply by exploiting these right shifts. However, where it kind of breaks down is where I start using 2's complements numbers. And the reason why is it truncates down and it actually makes these numbers round down. So looking at these same numbers here, when I shift 4 to the right, where it should be minus 771.25, it becomes minus 772, right? So rounding down when it's negative means it gets to be a bigger negative number, if that makes sense. And so we see the same thing here. Minus 48.2 all of a sudden becomes minus 49. In order to prevent this behavior from occurring, we make use of a bias value that we shift before we do the right shift. So that produces a roundup value. The expression for how C actually handles this is encoded right here. You see in the slide, but the concept is we actually shift it over. We actually we actually, here, let me show you. We'll actually introduce a bias that's then applied towards the term, that's added to the term before we do the right shift that then forces it to produce the value we want. So again, we're going to do this same shifts we did before with the same numbers, and we're going to introduce this bias term that is going to be applied towards it. And now when the bias is applied, it's going to produce the values that we'd expect. And again, this bias term is defined based off of this K inside this expression here. So notice it's not something we select. It's based off of whatever K is for our shifting terms. So it's expressed inside of this equation here, which ends up resulting in something that's very meaningful. That's why it's increasing when we're shifting X amount of bits, because it's readjusting it based off of how many bits you have to shift in order to truncate to a value that actually lines up between our fractional number and the integer representation in a signed format. So just know that there's a little extra logic that has to be implemented for our division to work when it's a signed number. And I think for the most part, that's it. That's we're finished for the integer arithmetic. We'll follow up with floating point logic next class. Does anyone have any questions in terms of what we covered today? Covered a lot. We covered a lot of the arithmetic stuff, which is going to be kind of like the backbone on how any kind of numerical processing works, at least when it's not in floating point numbers. And we'll cover that on Thursday. Excellent. Okay, I will let you all go because I took like 4 minutes over, but I did not want to stop on like the second to last slide.